All right. Good morning, everyone. Always fun to be the first slot of the day. It means we don't have the post-lunch snoozing. Hopefully the coffee's a new system. I'm here this morning to talk to you about space technology, which might seem a bit out of left field for a TasICT conference, but hopefully as we go along you'll see how it ties in, I think, quite well. Hi, I'm Mars Buttfield-Addison. You can find me online on most platforms as The Martian Life. I'm currently a PhD candidate at the University of Tasmania under the School of ICT and with CSIRO's Data 61. I'm also a freelancer. I've dabbled in everything from machine learning and GPU programming, app making. I make educational tools, code-along activities, all sorts of things. I love technology. I love teaching technology. I love telling people that they can do technology when they think it's too hard. And now I go around telling people they can do space technology even though they think it's too hard. My PhD is working with this awesome instrument right here. It's called the Australia Telescope Compact Array. It's up in northern New South Wales, and it's an array of 6 22-metre dishes separated by up to 6 kilometres that act together like one giant radio telescope to look at our skies. And I love doing this because I love domain-specific technologies and how if you dig deep under this thin veneer of general-purpose computing in the era that we're in now, there are still some of these old ways of you have built a machine for a very specific purpose. It has its own languages, its own paradigms, its own nuances, and I love how you can get to intimately know this sector. Today I'm going to talk to you about a few aspects of space technology and the state it's in Tasmania today. First is about strengths and opportunities. What things are unique about Tasmania that make us either really great at space already, or things we could leverage for space technologies. I'm going to give you a quick overview of some of the current and ongoing projects we've got going on. Unfortunately, as space is quite intrinsically linked with defence, there were quite a few projects that I contacted people about and they said we were not allowed to mention. And I'm then going to talk to you briefly about some of the skills that you might already have, probably already have in spades, that are actually really applicable to space as a sector. So you might be able to see some of those links to the things you're doing now and how that might be applied. So beginning with strengths and opportunities, I thought I'd start with a weird one. So Tasmania is the home of the Australian Antarctic Division, and we have an enormous slice of Antarctica that belongs to. It's lorded over by Australia, and this is an extreme and remote environment. And we've actually been using this to train astronauts and to run test programs for mental health and physical health of people in extreme environments for quite a long time. In fact, we've got partnerships going back to 1993, the year I was born, of these kinds of programs. We also have that hyperbaric chamber at the Royal Hobart that you might hear come out at every ministerial talk about space. We have that chamber that not everyone else has. Well, good luck. Good news about that chamber, we got a bigger one. We got a newer one. It does the hyperbarics even better. This does mean that we do have the infrastructure required for astronaut medicine and training, and we've actually been doing that quite a long time, but on behalf of other people. These are partnerships that we have going on with people like NASA, where we basically just give them an area. They go, you've got this remote station in Antarctica, we want to have remote stations so we don't have to keep sending our people to the desert. Can we send our people to your stations? And we say yes, but we don't really have any of that building an industry of our own as yet. Another aspect is down here in the southern hemisphere, we're actually quite south. We don't really think about it because we're only at 42 degrees south. It doesn't seem like we're anywhere near as north as some of the northern things up in Canada, but we're quite south actually, and we can see a completely different part of the sky. And if you look at these international networks of sensors, radio, optical, hybrid, laser, other, that look at the skies, almost all of them have no sensors that are as south as we are. We can just see different parts of the sky than they can see. It's actually more complicated than that. If you'll forgive me a brief segue into electromagnetics, this is our electromagnetic spectrum. It comes from very small wavelengths, very high frequency, to very large wavelengths, very low frequency. And this contains a whole bunch of different parts of the spectrum that we use for different things that we might think of as different things. So we've got all the way down with gamma rays, X-rays, UV that we use for some things because they can penetrate through our bodies, and we can use that to look at space because it can penetrate through dust really well. Visible light, which we've evolved to be able to sense because you'll see in a minute. Infrared, which we can use for some heat stuff, all the way up to radio and low frequency, which we basically can't observe very well because they have wavelengths that are larger than any of the sensors we could build. If we have a wave that's a kilometre wide, we'd have to build a very large sensor. And our Earth is precious. It's got this really unique atmosphere. It protects us from so much of this harmful radiation that's out there in space. And we have this lovely graph that tells you how much of our atmosphere absorbs each different part of the spectrum. If you look at this line, you can see that basically none of the lower end of the UV spectrum gets down to the ground. That's why we only get a little bit sunburnt, we don't get burnt to a crisp when we go outside, because our atmosphere protects us. We see quite a lot of visible light, which is why we're all for that. We can see near infrared, and then when we get up to radio, it's basically unimpeded, which is why radio is such a good way to look at the sky, and why often for things like infrared, we want to mount those sensors on telescopes so they don't have to look through the atmosphere. Down here in Tasmania, we have something unique. So if you look at a model of the Earth, we have the geographic south, which is the pole that we rotate around. As we rotate, we orbit the sun, and that's our south pole and our north pole. But then if you look at those graphs that look a little bit like these concentric circles of our magnetic field, our magnetic south pole is in a different spot. And the way that those two things are offset skews in the direction of Tasmania. This results in a really cool thing. In our upper atmosphere, we have this charged layer called the ionosphere. It is what lights up and gives us aurora down here in the south because it's thinner, so we can get that charge visible down on the ground. It's why we suffer slightly more radiation and higher UV down here in the south. But it also means, and disclaimer, this kind of has a day-night fluctuation. This is nighttime in our hemisphere, but still, over Tasmania, we have some of the lowest electron content on average in the world, which is why we have radio astronomers moving from all over the planet, to come to Tasmania to look at the skies. We can see the skies better. We're getting less scattering and we have less atmosphere to look through. We're getting a better look at the sky, not just a look at a different sky. So the University of Tasmania has embraced that over the last 60 years and operates some of the most powerful radio telescopes in the Southern Hemisphere. We also have quite a lot of optical telescopes, but I'm a big radio nerd, so I'm going to talk about the radio ones. We operate telescopes all over the country. So we have 12 metre dishes in Northern Territory and WA and down here in Hobart. We have a 30 metre in just outside of Adelaide. We have a 26 metre in Hobart. We have a 14 metre in Hobart, and now we have a 7.2 in the middle of Tasmania, which is about as many observatories as CSIRO operates in the country, and way more than anyone else operates in the country. The University of Tasmania has so many radio telescopes, we don't even know what to do with them all the time. They're actually idling most of the time, no matter how many cooperative projects we become part of. So we're writing more and more automation software to try and do something with them all the time, because sensors are usually the bottleneck for most universities. They don't have telescopes. They'd love to look at the sky, and we've just got them sitting there. That's actually why this 14 metre at the back has just signed up to a program called Skynet, very silly, where there's a STEM network coming out of the US where you can tap your telescope into this online scheduling system that lets high school and college students who are learning about astrophysics operate your telescopes, and we're one of, I think, only 2 or 3 radio telescopes in that network. It's really exciting. We have this great infrastructure. It's a really big deal. So that means that we have all that we need to do spacecraft monitoring and communications right here already on island and operated on island. It already exists, and in fact, there's no additional hardware needed. This one's a bit of a longer bow to draw. I think it's safe to say that we've all heard about things like INCAT, that we have incredible manufacture capabilities on the island. We receive awards from all over the world for things like our maritime and our machinery. So that tells me that we do have the resource collection and the complex manufacture capabilities to do things like on-island manufacture and operation. Yes, it is a different skill set, but it tells us we already have the foundations that we would need to go from there to learning how to make our own spacecraft. Maybe we're not going to go straight to building our own booster rockets, but making our own CubeSats, absolutely. We fab things on island. We have this expertise. We have people moving from all over the world to come here for our manufacture sector, and we could leverage that also. And across all of those sectors, we already have these partnerships with some of the most amazing space operators in the world, from public space agencies to private, from across the Western Hemisphere, the Eastern Hemisphere, the North Hemisphere, the South Hemisphere. We've now got our own space agency in Australia, which has already invested in Tasmania, putting their money where their mouth is. But it's not all golden. There are other programs, such as the SmartSat, which you might hear about if you go to Professor Jill's talk in 2 slots, about the Cooperative Research Centre for Small Satellite Research. This is a really cool research centre that is... most mainland universities are a member of this, and University of Tasmania is not. And there are a few of these programs where we've been left out a little bit, whether that means that we need to do a better job of establishing our capabilities and making that very clear to the mainland, or it's just a poor communications, whatever. So we have wins, we have lots of overseas connections, great things to leverage there, but we actually aren't that great at making connections inside of Australia. There's a lot of that state-to-state competition still. But it means that we already have some really amazing projects ongoing. And I thought I'd begin with this kind of quadrant system, just to kind of break down how these are different. So we have things that are research and technologies that we do for space, and we have research and technology that we do in space. This means that we have all the way down in the lower left quadrant, things that we do for space that are academic. Might be everything from a research route you has downloading some data from a telescope somewhere else and making a data analysis tool. That is technically a technology for space. It is academic, no one's going to buy it, probably isn't going to make much of an impact, but that is for space, and that is a step. And in the upper quadrant, on the right, industry in space, you get all the way up to manufacturing and launching your own rockets and having an astronaut program. And no one thinks that we're going to go straight from this to this, but it's nice to think of it as a linear progression where we can go from one and build on those as we get there. And I think that for quite a long time, like I said, we're quite well famous in the astronomy community. So it means that the for space academic side, where we're using sensors to look at space, to do space communications, we've already got those partnerships, we're already doing that, we've been doing it for decades. And in a few slides, you'll see all the different ways that we're starting to get into for space research and technologies in industry now, with some great support from the Tasmanian government and from the Australian Space Agency. But we are yet to operate anything in space of our own. We don't own any satellites, we don't operate any satellites, we don't manufacture any launch vehicles or spacecraft here. And that is presumably something that we would like to aim for in the future. Unfortunately, when I went around, there were a few projects scrubbed as late as very late evening last night. I had to scrub some projects. So there's some really cool things I'd love to talk to you about, but it is true that unfortunately space is seen as a contested domain. There are lots of links to defence. There are security concerns to talking about things that we're putting in space, and especially things that we're monitoring that other people have put in space that sees us as a vector for attack. So this is going to be sometimes light on the details. But we have a partnership between Henselt and the University of Tasmania. You may have seen in the news. Henselt is a world-famous radar company from Germany that has set up an office right next to Post Street Social on the waterfront, and they are looking at how they can better our space jump and spacecraft tracking capabilities. At the moment, that has taken the form of buying new mounts for our telescopes, where we operate an observatory in the middle of Tasmania, where it's got less light pollution. We've got optical telescopes here, and we're looking at how we can make a hybrid approach of looking at the skies. So if you think about optical, like if you take a snapshot of something, if you know exactly which way you're facing, and you can see exactly where that thing is in the frame of your camera, you have a very good idea of the angle of that thing to you, but maybe not the distance. You have to infer the depth. With a radar, because you get a ping in return, but like sonar, that means you get great depth, but you might not have great angular resolution. So if you combine the angular precision of optical and the depth precision of radar, you can get a much better read on the position of something. So we're trying to get those two kinds of systems, get them to have great relative precision, combine them together so we can get a greater look at the skies. So in the middle of Tasmania, I'm working with Henselt. We're looking at hybrid detectors for space objects. It's a bit biased. Some of my team at the University of Tasmania in physics work on space weather, and they came from some of the correlator centres in the Netherlands and in Finland, working on projects that tracked space probes. This software first came out of the Higgins landing as they dropped a probe on Titan in maybe 2008. And since then has only grown. This is called software spectrometer, which is to take that raw feed of just voltages coming off a telescope as it gets digitized to then make it into sensible information as we have to account for the Earth's rotation and everything during those observations. And to make software for that is quite complicated, but relatively stable no matter what sensors you're using. So this is software that's been developed in the University of Tasmania from people who came from all over the world to work there. That's now used by telescopes and observatories all over the world. So like all of the Korean ELBI network runs on this software, and they've got them running in the US, they've got them running in Europe. It's really awesome. And it's open source because quite often in academia you don't have an incentive to put something behind a paywall, which is nice. We've got some really great partnerships with people like Ozscope. There's this cool program called Positioning Australia, which is an Australian government initiative to have better timing and precision systems. So we have this idea of what the Earth looks like, called the terrestrial reference frame, where we keep a model of the altitude of the Earth and how the different plates move and everything. We need that for really important things like GPS and timing, keeping our clocks in sync, knowing about relative positions of sensors we use to look at the sky. It's really important that we keep a really good model of what the Earth looks like at any given time, and that feels that we We call it geodesy, which is where we can get different telescopes that we know very precisely their relative distance, and we point them at really stable deep space objects like black holes, and then we can measure how the delay between those two telescopes changes, and that tells us how the position of those two telescopes is changing relative to each other. And Australia is a great contributor to worldwide geodesy. We've got partnerships all over the world. Basically, that map I showed you earlier of sensors all over the world, we're the biggest part of that network. We even had a Japanese delegation down yesterday talking about how we can contribute even more to the international reference frame. This is this really awesome scientist from UTAS called Lucia McCallum, who heads up a team there in VLBI and geodesy research, and they have these telescopes running 4 times a week, 24 hours a day. Some of us PhD students run them all night, every night, making sure that they're collecting all this information to keep an updated model of the Earth. And they've got current partnerships with Geosciences Australia to get high-speed links between these observatories that are running those experiments. So the one up in Northern Territory, the one down near Perth, the one in Hobart, and then to the Supercomputer Centre in Canberra. This is a project that has just been approved. It should be maybe a 3-year timeline that we're going to get high-speed links, which means that instead of collecting data in the Northern Territory and Perth, pulling out those hard drives and mailing them to Hobart for correlation, and then us uploading that to the internet to get those updated models, now they'll be able to be done live, straight in the supercomputer, straight uploaded to the international reference frame. Awesome. The arrows on the side are also because for this, the University of Tasmania also quite often operates the telescopes on behalf of Warkworth in New Zealand and Hartwestuk in South Africa, because we're so good at it. You might notice shortly that bandwidth is a common theme. It is unfortunate that while we have really great internet on island, our connection out of island is finite. So you'll see many of these projects butt up against what we can do with the Basslink, and so many of these ideas come from let's upgrade our capacity to get to and from the mainland or to and from anywhere else, because if we turned our telescopes on full precision all the time, we would take over all of the capacity of Basslink, all the time. And the fact that we're not doing that is a kindness. So, the Australian Space Agency also, like I said, put their money where their mouth is, and they gave us some money to upgrade our infrastructure, which is actually where this really cool dish came from at BISDT, or Green Hill Observatory in the middle of Tasmania. This is it getting assembled. I didn't want to put it in the complicated, put in a video in your slides, otherwise you'd see that the cool thing about this dish, even though it's not as big as our other ones, is it slews really fast. So if you've seen that big dish near the airport, it's really large, it weighs tons and tons and tons, and so to point it in a different way takes a really long time, and that's fine if you're looking at a black hole in deep space. It doesn't really need to change points. But if you want to track a spacecraft as it goes overhead, you need to be able to track as fast as it moves. We didn't have anything with that capability, and now we do. One of the other people in the country. Actually, I think it's one of the fastest slowing instruments in the country. Maybe the at the moment. Don't quote me on that. It's very fast. It's shocking to watch because it's also very heavy. So you would not want to stand underneath it. There are lots of barbed wire fences around it, but it's very cool infrastructure. Also, at the end of June this year, a round shut for the first round of the Space Technology Seed Fund, which is a state government initiative to fund partnerships between companies to do space technology stuff. So if you were a company and you could find another company to partner with and you wanted to make something space related, you could get match funding up to $100,000 to do that. I put here, this is the second round, so at the end of this talk, you're convinced that you totally want to do space stuff. I'll show you the slide again and you can apply. It's very good. So under that, unfortunately I was going to talk about how you're going to see from Pivot Maritime today, but their talk has been cancelled, unfortunately. But Pivot Maritime, you might know from the TasICT Awards, and lots of things, for the fact that they build ship analogues, they build these ship helms with all the proper controls. Shaking your head. Like that is what they do, I swear. Sat beside him the other day. So they make ship helm analogues, and so they do it for training reasons. So they have like this fake ship, and you can operate the bridge of a ship without the threat of crashing a really expensive ship. How great is that? We have Fortify Edge, which has like the edge devices for biometrics, which has previously been applied to military. So you want to know where your troops are, you want to know that if they're accessing something, you can identify them by their biometrics, and they've got the authority to access that. You also want to know how they're doing, so it's also human condition monitoring. And they've partnered up to do something for space. So the idea is we want to be able to train astronauts not just in extreme environments, but also in spacecraft analogues. And wouldn't it be great if while we're doing that, we could also monitor how they're physically reacting to the stress? How are they doing? And we can do that before and also when they're in space, use that biometric monitoring to see how they're doing. It's an awesome, awesome project. This one's my baby. The University of Tasmania has partnered with the supercomputer firm you might have heard of just outside Launceston, Thermos. They've got one of the greenest data centers in the world. They've got all this new technology for how they cool their GPUs. It's a really cool company. And the University of Tasmania has all these cool telescopes. We're kind of capping out our processing capabilities. And yes, we do have the high performance center at UTAS, but also it's quite silly because they don't think that we're big data enough. At least they do genomics, which is an order of magnitude bigger. So we made this partnership so that then we can make high-speed links from our telescopes to Thermos to do real-time tracking. So where the telescopes are collecting data to look for astronomy and geodesy reasons, and the astronomy stuff is being processed in Hobart, and the geodesy stuff is being processed in Canberra because of that great Geosciences Australia partnership, then we can turf it to Thermos to do processing for spacecraft tracking, so that we're getting that same data delegated to different places, looking for different things because they need to be correlated in different ways, which means we just triple the amount of processing that we need to do to get 3 data products out. But it means that we can start managing some of this, which we're actually contributing quite a lot to from Tasmania, but previously it's been as sensors operating on behalf of other space agencies, whereas now we're going to be collecting our own data, which is also something we can commercialise, which is great. So, hopefully by this point you're convinced that space is cool and that we are doing some pretty cool things, and now I'm here to tell you that you can do these cool things, because you can put your hand up if you think you have any of these skills. We do need edge and embedded computing. We need to have low-power devices who can do processing on-device. We need to have things that can work in a really hardware-specific environment. We need things that can work exposed to radiation and heat and cold, and we need them to work very, very far away from your control. For that same reason, we need autonomy. We need things that work without guidance, that know how to respond dynamically to these changing conditions we might not be able to foresee in space, but that will respond like a human would, or sensibly, or at least safely, like fail-safe. So we need AI and machine learning made by people who are conscious of those risks and of the impact it could have on people who are operating these technologies in space. We need high-performance computing because, like I said, you've seen all the different ways that we're capped by bandwidth. We need this processing power, and it's not just the fact that we can throw more GPUs at it, it's too expensive. We need to be smart about our processing. We need to be data-specific. We need to be hardware-specific. And we need to be great at the scale-up and scale-down on-demand processing, so that we can use our bandwidth, especially to and from Ireland, in a smart way. We need cybersecurity, and this one's a bit on the nose because 2 sessions from now, Jill will be talking to you about some of the concerns of infrastructure in and for space and how they have unique cybersecurity concerns, and her management of the SmartSat CRC has a lot of focus on cybersecurity, because while we didn't talk about it, a few years ago I was at an Engineers Australia conference and I told someone about how I'd been writing and reading about hacking of satellites, and he looked at me and he went, I've been making satellites for decades, no one can hack a satellite, and now we're hearing about people hacking satellites. You can hack satellites. They're a remote system that their configuration is known in advance, they're quite difficult to update, they're up there, you can't really get physical access, but that also means that the only way that they can communicate is remotely. If you can spoof a ground command, it will do whatever you want. It's incredibly dangerous, and we're starting to see the risks of that now. Even as we think that our satellites get smarter, we've got also more and more people who are able to put their satellites in space. We don't have standards, we're not agreeing on protocols. So there are things where, like, a group of university students from Melbourne University have put their own CubeSat in space. It's up there in the same domain as everyone else and had critical space-based infrastructure that we need for our daily lives. It could do just as much damage if deorbited irresponsibly. And yet, do you think it has as good security controls as something made by an army? Probably not. It's a really big concern. And not only that, but we don't have courses or anything to teach you about space-based cybersecurity because we don't even know what we're going to face in that domain. So that's an incredible one to watch. This is one that we don't often get mentioned, but human-computer interaction and user experience. This is a really creepy robot that they put on the ISS to try and keep the astronauts companion. It's creepy, and this is why. There are unique usability constraints in space. There are going to be people wearing thick gloves and not being able to move correctly. There are people who are under mental and physical stress, and they're going to have unique concerns about the things that they can use, the things that they need in space, and they rely on so much technology for their day-to-day lives to be able to eat, to be able to breathe, to be able to do their science in space. So we need to think about the unique ways that we can make their life easier, because we all know that good UX is invisible and not this. And I wanted to do this talk about how your skills are applicable to this space, because ask me how I know. I have a bachelor from the School of ICT at UTAS. I did honours in not anything about space. I came from analysing social media data and stuff, and I went to CSIRO and I went, I have these skills, I do machine learning, I do data, I love programming languages, weird ones especially, what can I do? And they went, we really need someone to do space. I stumbled into this domain and found out it was the absolute passion of my life afterwards. But you can do this. If you have these skills, we need them now. I guarantee you, if you're looking at this and going, I'm not really an aerospace person, I guarantee you there's not a more aerospace person just hanging around not doing it in Tasmania. We are it. We are the team. If we're going to build a space industry here, then it's us. And I really want people to believe that. So, if you have any ideas for your companies, for projects, for things that you can contribute, whether it's for astronauts looking at their mental physical health, if you're looking at environments for space, if you're looking at gadgets for space, if you're looking at sensors for spacecraft, if you're looking at how to look at space, anything to do with space, take a photo of this slide and go look at state growth. They might give you money. So, I've left a little bit of time at the end because I thought that we might have some questions and have a little bit of a chat about it. Does anyone have any questions?